So while it turns on, I was just thinking that last time, the first difference between transformer and the DeepSeek model was the instead of using the fast feed-forward neural network, after the attention head, they started using the mixture of experts.
Mm-hmm.
And in mixture of experts, they had some shared nodes and then some
Share experts
shared
and
then
routed
some
experts.
and routed experts.
Mm-hmm.
The shared expert would all be the ones that will always be turned on, and the routed experts would be turned on based on based on certain algorithm that we talked about. And it'll pick up which routed experts to go to
Yeah.
in the router that we discussed some ideas on how that routing works and how that they manually put in some bias so that certain routers where data didn't flow through,
Mm-hmm.
data will flow through. So those routers also get trained
Mm-hmm.
during training.
Yeah.
Then,
So they are balanced, chain
yeah,
balanced. Yeah.
and then comes the multi-head latent attention, where
Mm-hmm.
I think if you go down a little because the screen's not very clear. Yep. Here we had the input hidden layer, where this input hidden layer would be the
Hidden input from
the RMS norm, I believe.
hidden input, normal hidden input, like we going through layer, we have hidden input all from embedding, right?
Yep.
Embedding.
So that embedding basically is, let's say if we have got a sentence, whatever that sentence is, that this is an apple, let's say. So the embedding for this and is apple and all the tokenized embedded vectors.
Yeah.
The input hidden here, input hidden is the all of those joined together.
Correct. So it's a batch size and then sequence length, then dim.
Okay, so it's not only just one sentence, it's all the sentence in that batch.
Correct. It's
So
a batch.
normally how big is a batch normally every time?
It depends on your hardware. So you can put like a 4 batch depending on your GPU size.
GPU. Okay. But normally, what is the usual size? Let's say when they actually trained, how long they take? Like a really big batch?
You mean the sequence length or just
No,
batch?
no, the batch.
Batch size? Batch size is really depending on your GPU
Hardware.
size. Yeah, if
Okay, so
you
it can go from 4 to some like even 100.
100, I think in there could be 8 or
Okay.
yeah, it
Okay,
really
I see.
depending on the and your dimension also. Yeah.
Okay. So this input hidden layer now contains the batch size number of sentences, and for each sentence, for each input, all of the tokenized embeddings, and so it is embedding size times sequence length times batch size.
Correct.
And what about the padding? Will it have padding?
Yeah, there is a padding. If
Padding, okay. If
you
the
said
sequence
in
is small.
each batch there are sentences. Actually,
Yep.
it's not a single sentence. It's multiple sentence joined together so that
Yeah.
reach.
So to fill so include, so there is least amount of padding and most of the data is extracted.
Correct. Yeah.
That's a good idea. So once that comes through, that is then converted into a latent representation, which is sort of like a compressed representation of the whole thing.
Correct.
But my question over there, so these are some of the questions I had yesterday. I think I'll just bring it up now. So when we are doing that compression,
Mhm.
are we doing a compression at a certain dimension, or like the input hidden layer, let's say, was
Yeah, we are doing compression in the dimension.
which
So
which dimension?
you see here, let's see. So here you see we
Hmm.
have batch size, sequence length, and dimension, right?
Uh,
When
what is this dimension? It was batch
this
length.
is the embedding dimension. The
Yeah, embedding dimension. Yeah, yeah, yeah. So
For
we do
example,
it at
is
embedding level.
yeah, it's 7,000, right?
Oh, is this
7,000.
7,000 the embedding dimension?
Yeah, embedding dimension is quite large, right?
Huge. It is
Yeah,
quite large. Yeah, yeah, yeah.
yeah, but
Because
for
like
the
we were doing it like at in most of the word to vector, those sort of things, we were thinking of 200 or 300.
correct, and that's not LLM. So
Yep.
in industry, I think they
They
use
use like
bigger, yeah,
more and
so that
more,
yeah have more meaning there,
more
can
meaning.
catch
Got it.
more meaning, yeah.
Right. And now they
So
this down projection is the compression.
Yeah, correct. So we down
Okay.
project into the NORA rank. Formerly there's a paper is called LoRa. LoRa is a abbreviation for rank uh, low rank metric something compression or something. Let me search that up.
Is that the same thing that they use to compress in transformers from the value vector that is broken down into two
Uh,
vectors?
no, it's a different concept. So it's a
Okay. Okay. This is something I
low
don't know
rank,
about.
yeah, low rank adaptation. Low rank
Mm.
adaptation basically it's transformer has a like attention metric. There's
Mm.
another that low rank. It's concept from our math. So
Yeah,
in
I
math,
did.
the PCA, right?
Yep, yep.
Yeah, it's similar to that. They
Okay.
think that we don't need so many dimensions to
Mhm,
capture.
mhm, mhm.
Yeah,
Then, if we go
there's
back to the diagram,
mm.
what difference will it make if
So the
we
difference
if
is here. So you have 7,000 dimension before, right?
yep,
Then if you down project into LoRa rank, so
yep,
it's only have 500.
5.
Yeah,
Okay, okay. Then my question is that what if our embedding dimension is 512?
our embedding dimension.
Is
Embedding
512 and we don't need to do LoRa anymore?
uh
What is that? What difference will it make that because you first have, you are training such a long dimension, so many
mhm,
dimensions for embedding, and
mhm.
then you just down projecting. You never up
Correct,
project.
correct. I think I haven't got like real experience or training those big real commercial large language model. But I
I
think
see.
what it's trying to do is you using redundant to easily
Hmm.
learn, right?
Yep.
Easily learn first, then you compress it.
Hmm.
Yeah.
Hmm.
So
Hmm.
you try to learn more, then you compress. It's
If
easier.
we go slightly up when the screen is complete, so when we down project, do we ever up project back?
Yeah. We up project to like head,
Hmm.
multi head. So each head learning a different aspect, which is the same concept
Which
from
is same as,
transformer.
yeah, yeah,
Yeah,
yeah.
transformer. Yeah,
So after down project, we send it to all the different multi heads.
correct. We up project so that it's the same as a transformer. So we
Okay,
have multi head.
right. When you say up project,
Mhm.
does it mean that you go from the lower rank representation of the matrix, the number of dimension increases?
No, it
No.
it's it's increasing, but increasing into multi-head. The dimension it is increased. You see here, if we time
Oh, it's
this
just a repetition then.
repetition, what do you mean by repetition?
I meant when you have down projection and you
Mhm.
have a matrix which has got dimension, time, Q, LoRa, rank.
When we have a low down project, it become a batch size times
Batch size,
sequence
sequence length, time, Q, LoRa.
LoRa rank.
Yep.
LoRa rank.
Now, instead of this LoRa rank is basically a replacement from dimensions to LoRa rank. So instead
Correct.
of 7,000, now you have 500.
Yeah, correct.
And then now when you pass this to multi-head, you passing exactly the same thing to all the heads.
Correct.
Right?
So
And
this one will expand to multi-head plus
because okay,
multi-head.
because then is the output from the multi-head.
Correct. Formally, what we do is we are using this one directly to
Directly into
multi-head.
multi-head.
Correct.
I see now. I see. Okay, so when you say up projection, I got confused. I thought up projection meant going back to the original dimension size, but actually this up projection is because there are
Multi-head.
so many multi-heads. All of the output from the multi-heads is sort of combined together.
Correct.
In sort of like a tensor, and that tensor that increases the dimension in number n heads in that dimension. It gets multiplied by whatever that number is.
Yeah, correct. And we are doing LoRa rank here is to reduce the cache size, right? We mentioned last time. So that it has higher capacity to do like bigger batch size and longer sequence length.
So the Q LoRa rank and the KV LoRa ranks are different.
Yeah, they are different. Q is for query. They are same concept, but they use different for different things.
And it's very interesting that they used Q to be higher, 1500, whereas KV to be lower. And KV will include query key and value.
Correct. Here it's the main intention is to reduce the cache size because we are cache KV. We are cache KV, so this is the main point we want to compress.
And what do you mean? Why do we cache KV?
KV because you know the KV cache after transformer. I think in a NAMR or some former papers, but from NAMR it start using KV cache. KV cache. Think KV cache. Let me try to find a simple diagram. See if I can explain it quickly. KV cache. KV cache. Let's see this one. Let me explain this one. KV cache is for inference. It's used in inference time. So it's the method to speed up the inference, right? Only useful in inference because training is not useful. We are always the whole batch. So in inference time, for example, we have this sentence, right? We have this sentence. Then in the first time when we input LLM, it will dot with its own key and its own value because it's the first token, right? Let's one word as one token for now. Then in the second one, inference, when we say inference, it's dot with LLM and inference key. And the value is also LLM and inference, right?
Right.
So
and the third one.
if we catch catch the formal thing we have done, we save time, right?
Yeah, I see, I see.
And that's why you see it's going when we go in third position, then become optimization, but the key part and the value part is actually LLM inference optimization.
Yeah. Oh.
Yeah.
Because this gets the key value part gets used at
Multiple times.
every step. Yeah, every token again and again. When you cache it, you can save a lot of memory that we don't have to go through.
Yeah, we save time to do those projection or something
It's
like
more of a computational demand than the algorithm.
correct. Inference optimization.
Got it.
Inference optimization. It's only good for inference because in the training time we input large everything there. It's not one token by one token, right? But in inference time we are lax token generator.
Yep.
Yeah.
Okay. Okay. I
Okay.
think that,
So
go ahead now. I'm sorry, I took a lot of time. Sorry, Nat.
no. It's okay. Questions is good so that we clear. Okay. Let's start. Before we start, let me mention one thing that I think I forgot last time. Is for the as you mentioned for the buyer's term we use in the MOE.
Yep.
Buyer's term, right? We using buyer's term to alter. Let me split screen.
The weights.
We use buyer's term to balance, right? To help balancing MOE experts, right?
That's right.
And we add into the score so that it's to balance. But before, but buyer's term, we also have place to adjust it. So in each batch, we will adjust this buyer's term. Adjust by its learning rate. Learning rate is setting here. Is setting here, right? No balancing, adjusting, adjustment step size, U, right?
Yep.
We set to something. Then we adjust it in each batch. How we adjust it? We are using this step size times whether the token number of token received by this expert is lower than mean or bigger than mean.
Oh, that's a very good idea. Very good.
Yeah. So it's
That
very
is beautiful.
Very simple. Is also very effective.
That is,
Right?
yeah, it's really beautiful. It just makes the job of load balancing such an easy thing to do. Otherwise, load balancing can become complicated.
Yeah, complicated because we need to add like north term to the main node.
Yeah, exactly. This is like just count. If it is lower than average, just increase. It's like a hack.
Yeah.
Very good. Yeah.
Yeah, and this part I implement myself. There could be some mistake, but the main idea is there. I'm implementing according to the paper. There's a former paper, so there's a like a pseudocode.
Oh, I see. Okay.
Yeah.
So you're using that to implement.
Yeah. I implement the official source code doesn't include this part.
Oh, so how is the official code doing the load balancing?
There isn't. Official code only release the inference code.
Oh.
And there isn't training code. And also for the MTP part, I'm going to show is also I wrote it. I reference some other resources and reference the how.
Why are you writing it yourself?
Pardon?
Why are you writing? To understand it better? Is it
Yeah. But this is important part. It's quite important. Otherwise, you only can read in the paper, right?
Yeah,
You
yeah.
don't have a concrete thing to discuss, to talk about. Yeah. Yeah.
So now this is a good thing because this, I don't think that your job forces you to write it again. You're doing it on your own.
The next step will, for me, will be I will try to train the former GPT-2, right?
Yeah.
I will train the MOE1, I mean the shrinked
Yeah.
DeepSeek V3 architecture model. Then I can compare, see in a smaller scale if
Mm.
they have different like performance or not.
Oh, are you gonna train your own
Yeah, I will
GPT,
train a smaller one. Otherwise,
smaller one? Yeah.
yeah,
The
yeah,
bigger one, yeah, you cannot. But even
yeah,
for
we
the
can.
smaller one, when you're going to do it, are you going to use the all of the DeepSeek and all of the GPT-2 the way they are, or are you going to create your own hybrids
It's GPT-2
from the
from Andrea
OpenAI?
Karpathy,
Yep,
and
yep.
I
Oh,
will adjust it a little bit for training.
I see. Okay.
Yeah, just do a comparison just for like personal interest. Yeah.
That's very good. Okay. All right. Let's go.
Okay, let's keep going. So last time we discussed I think the higher concept on multi-head latent attention, right?
Mm,
We already go through all those and the high level flow. Then today I think we go through we already discussed the
yes.
metric associativity. So it's mapped to
Mm,
associativity implementation in DeepSeek. And
yep.
if we don't do associativity, then it becomes naive version. So we explain
Mm,
up till here. So
mm.
let's have a look in the source code first before we go to the absorbed version.
Oh, okay. There are three versions.
Yeah, three
Okay.
versions. But in the third version, in official code, there isn't official code. Official code only contain a naive version and the associative. The third version they explain in the paper, but they
I
don't
see.
have,
They don't have the code.
yeah, don't have code.
Mm,
Let's go through the code for the naive and associative version.
mhm.
Mm. So this one will be against here. So the naive one is very simple. Just source code and the diagram is one-to-one mapping.
Yep.
So we have done projection metric for the Q and up projection metric for Q.
Yep.
And the same for the KV. We have down and up, right? Projection metric. And finally, we have a standard output projection, and the softmax scale is the head dim square root. So it's the same as a transformer, head dim square root of head dim.
Yep.
Okay, then
Yep.
yeah. Faham, do you have any
No,
question?
I remember that from the
Okay,
under root dimension.
correct,
Under
correct.
root DK.
Mm.
That's the same thing. Yeah, okay.
Yeah, correct. So we also have key cache and V cache, right?
Yep.
V cache is the batch size, sequence length, number head, and dimension, head dimension.
Mm,
Mm, okay. Then first step is we down project Q, up project Q. Then we split, we rearrange Q and we split Q. So it's mapped to down project diagram here, down project, then up project, then split into in position encoding part and the non-position encoding part.
Yep.
Then for key, we are doing similar thing. We down project. We split. We down project. We split into KV latent and the key encoding part. Yeah.
This one is the one, because there is another split happens after the down projection from the latency.
It's here. It's here.
Yep.
Later.
So that's one split. And then this, the first step where it goes to the rope is just directly goes in. No down projection here.
Correct. You see here is a KV NORA rank plus rope heading. All right. Yeah, so some part going here, some part going here. So we split. Then key position encoding going through rotary position embedding, right? Yeah. Then we for the KV part, we are doing up projection, right? Up projection to be multi-head. Yeah, then we rearrange to be multi-head, and then we split into key part and value part. It's directly mapping to the diagram. Then we concat the key part with position encoding part and the non-position encoding part. We concat, but before we concat, the positional encoding part will be replicated will be expanded to be multi-head. You see, before it only has one, right?
One head,
yeah. So it replicate to match the long position embedding part, which has multi-head, right? So we concat. Then we put this key and the value into cache because this part is only meaningful for inference, right?
Yep, that's
As
right.
we showed before in the KV cache, is one by one adding current into previous cache, right?
Right, makes sense. Now, when we do that apply rope, the part that does not go through the compression, LoRa compression, is that dimension same as what comes out of the multi-head from the K, which gets concatenated together?
Sorry, which part?
Like here on the left one, the middle one, apply rope, the center one.
You mean here?
Yep. So what comes out of here and what comes out of the one on the right, this one, are the dimensions same? Can they be actually combined together?
The dimension is not the same. They are concat. You see the high flow here. This has no positional encoding.
It has no positional encoding. Yes.
Yeah, this head dim is bigger. It's bigger. I will explain the intention. My understanding. Yeah. You see here, this one is bigger, 2 times bigger than rope head dim, right? So they concat to become the final dimension here is they plus together, so become 192.
Oh, you just add on top of it.
Yeah, they concat together. They concat, not add together.
Not add. Oh, I see. Okay.
Yeah, it become 192. Yeah. So this part is slightly smaller because its purpose is to capture like positional information, right?
That's right.
Positional information. This part is to catch the main meaning. Yeah, and this part is the part that we wanted to accelerate because when we discuss the absorption, we will discuss it. It's the main part we want to absorb, so that we speed up the inference time.
I see what you mean.
Yeah. Okay. Then we do a standard like attention score. So Q times key, this key from cache, right? Q times key, so we got a score. Then we normalize it, right? We apply the mask, we normalize it. Then finally the score is score times value. So it's a weighted sum of value, right? Then finally we do projection output, right? So those steps are standard from transformer. Any question?
No.
Okay. So here I use INOPS library so that it's easier to understand. So we can write out here. For example, here, batch size, sequence length, number head, then QK head dim, then times this. So it's obvious. Okay. Then we go through the associative version. So this part, some of the code I rename it so that it's easier to understand in official code. And I think the name for metric I feel not that easy to understand, but we will come back to skim through all the official code later.
Yes.
Okay, then we go to the associative. Associative, we said that the order we multiply the metric matters, right? It can result in NAS operation and the storage cost, as we said before. So this part is the same as the naive version, but with slight adjustment for the metric multiplication. So this part is the exact similar. Only difference is here. We have KV cache, and we have key position embedding cache. So the cache is mapping to exactly this diagram. So we only cache here and here. Right. In the naive version, we are actually caching the multi-head version. You see here, it's batch size, sequence length, number head, then head dim, right? But in here we only cache batch size, sequence length, then KV LoRa, right? This is
So
our.
every time, so are we going to do it every time?
Sorry, we are going to do every time. What do you mean?
So how will we use the cache?
Yeah, I will show you later. So we only cache in the diagram. You see here, the naive version, I think, is what the former KV cache do is caching the projected multi-head version. Like in the NAMR is caching the projected version is a multi-head version, like the naive one here, right? But in in DeepSeek, because we have latent representation, the compressed version, so we can cache the compressed versions to save the storage, right? Yeah, that's the intention. So here is mapped to the diagram. We are caching the latent representation. So here it is not yet up projected into multi-head. It's latent presentation, right? And we also have the part that for the position embedding. So it's here. So we have batch size, sequence length, and the rope head dim. Yeah, let's go through from here. So this is the same down project, up project, then rearrange split. And this part, we have a down project, apply, then put into a KV cache, and then get out from KV cache. But here we cache the, you see, we are caching the down projection. It's caching before up projection, right? We are not caching multi-head version. We are caching the down projection, then apply a rotary position embedding. After we applied rotary position embedding, we cache the we cache the key. Yeah, the value we just cache the down project version here. We cache it. Then the main step is here. We are time the queue with up projection metric first. So remember here, rearranged. So before the naive version, we are up project the key so that it become multi-head, right? Then Q is also multi-head. So we multiply together after we up project into multi-head. But when we rearrange, we doing this, we save the cost. We multiply the up projection metric for key with Q first before we multiply the key. Yeah, we change the order we doing the metric multiplication. So we do this first. Maybe I go to this source code to compare. So before before this part, this key is already a multi-head. You see here. You see here, key is already multi-head. We up project. Let's see. You see here, we KV we down project, then we up project, right? Up project. Then we split out the K, and the K we concat. So this K is already multi-head, right? Multi-head consists of no position encoding and rope encoding part, right? And it's a multi-head. Then this multi-head multiply with Q. You see here, it's already multi-head and a Q multi-head. Yeah. Right? But here we multiply the Q, which is multi-head, but we multiply with up projection metric. We are not doing up projection with key first and multiply with Q, but we do Q times up projection metric first. So we finish the associative first, then we using the resulting associative metric multiplied with key, which is the down projected key, right?
Yes.
From KV cache. Okay. Then it's similar for value. We arrange the order of multiplication. So it's here. So before we doing the value part, we doing this is value part. Value part we up project into multi-head value, right? Then we doing attention, then output. But now we do this first before we up project into multi-head. So just order alteration. Okay. This code I will send you the document so that you can look in detail. You just alter the metric multiplication. Okay. Okay. Then we talk about the absorption, metric absorption. So in the paper, there's a section that mentioned that if we apply rope for the keys, this key is like latent representation, then up projection in the equation 10, and a couple it will coupled with position sensitive rope metric. In this way, that key up projection cannot be absorbed into WQ since rope metric related to currently generating token will lie between this metric, right? Does not obey commutative law. As a result, what is saying that if rope part is involved in the multiplication, we cannot absorb. Let's see. I put an example here. So what we do for the attention, we are doing this is nope Q. Nope metric for Q, right? It's rotary position encoding metric Q, right? For Q, for query. So we normally do attention is Q part times key, right?
Right.
Dot key. So Q, what is Q? Q is the Q, the input vector. This should be input vector. Should be X. Should be X. Let me change a little bit. Here. Let me check. I'm not sure I put it where. Let's explain here. I think it's here. Let me check. Oh, it's here. This actually the same. It's just input X. This part is input, but it's up till this current token. So it's a input we project into Q space, right? It's the input we project into the Q. So this become QI, right? These two things become QI. these two things become K, right? So it's the
Yes.
input representation, hidden state of input project into a Q space. Then we rotate it. We rotate it with the rotation metric, right? Then the K part is the same. Input we project into K space. Then we do the rotation to the key. Then we multiply together. So this is the concept similar to QI before. QI dot product with KI, right? KI, right? This is what we do before, right?
Got it. Yep.
So what it's saying is each time at least you see here, for example, QI here. QI, if we are doing this sentence, for example, if we are doing this sentence, QI each time, first time where comes in, second time is the, then third time is boxed. So this I is keep changing, right? In the inference time, or
Yep.
the whole part, this whole part optimization is for the inference time only. It's not for training time, for inference time. So each time in inference time, we generate next token. So the position for this R rotation metric is keep changing for the Q, right? For here also, there is a concatenation into it. This is cache, right? So the cache we have for example, if the current I is at 4 position, is at these vectors, right? Word vectors, then this I is at 4. And this key cache will have previous 3 words, then plus the current will be put into cache, right? Yeah. So this part is keep changing. The first where it will at 0 position. The second it will become second position, right? So if we multiply together, it becomes this. So this part is keep changing. So we will not be able to absorb this whole thing, right? Because this part is changing. That's what it's trying to say. So it says that up projection metric for K cannot be absorbed into Q, which means this K up projection K cannot be absorbed into this Q, right? That's what it's trying to say, because this part is changing. So we will not be able to absorb and pre-calculate for this one as a single metric. What it's trying to do is to try to multiply together so that to save the time. Because each time when we doing the inference, we need to multiply these two metrics. So if we can pre-calculate, pre-absorb, calculate these two metric as a single metric, then we save time, right? Yeah.
Yes, right.
So it's saying that if we involve in the rope part, we won't be able to do this. So DeepSeek approach is to decouple the rope part. So the rope part become independent. So the long rope part will become simpler. So the long rope part no longer involve the rotation metric. It only has the normal. So this metric after training, they are fixed, right?
Right.
The Q metric and the key metric, they are fixed. So
Mm.
it will be able to be pre-multiplied together, absorbed, right? This what it means, the absorption. We pre-calculate this as a single metric to speed up the inference, right? Let's also explain, I think Farham asked before, why we have to split, right? We have to split the two paths. The lobe path. Normal transformer, we don't have this to split and concatenate. One of the reasons we split is because we want to split out the positional encoding part so that we can speed up. So so here for the code, what we do here is let me absorption version. So what we do here for the non-positional encoding part, we apply the absorption, because non-position encoding part also has a larger dimension, right? Larger dimension. We said here. We said before. You see in the diagram. In the diagram here, the positional encoding head dim is twice bigger than rope part. Yeah. So if we save the time here, meaning that we save the most time, right? So the rope part, we apply absorption. Formally is Q up projection, K up projection. Then we time together, right? We multiply together. But now we adjust. We open the bracket. Then we absorb these two metric. Then these two metric become absorbed version, right? This one is pre-calculated version for these two metric, right? And for the value part is also doing something. You see here. See in the paper. In the paper, there are two places is trying to do the absorption. One place is the KQ part, right? Key and the value part, key and the query part. The other is when we doing the, unfortunately, due to the associative law of metric multiplication, we can absorb this one into here. I think we can't. I think this comment is cut from paper or not. Here should mean we can't. We can't absorb this into here and cannot absorb this V value up projection into output, right? Into output.
I
so
see.
there are two here. It's a key and a Q cannot absorb, and the value and the output cannot absorb. So here, this part is try to absorb the key and the Q, and this part is try to absorb the value into output. So here before is the weighted value, and then up projection, then output. Then combine these two together into a absorbed metric. Yeah. So in the source code,
this is your own source code. You wrote that.
yeah, I wrote it.
Mm.
It hasn't passed the unit test, but the main concept is here. Once we train a network, we pre-calculate those metric. Yeah, we pre-calculate the absorption version. Then during the inference time, we don't need to time that two metric anymore. We just use pre-absorbed version in the QK and also in the value output. Yeah. Then all other code is similar to the associative version. Yeah. Any question? Okay. No, we continue. So the next one is the multi-token prediction. Multi-token prediction. We go through the diagram from the paper first. We quickly go through because this one is a little bit complicated. Then we go through the higher level flow. I draw it only for single token. Then we come back to understand their intention. Okay. So multi-token prediction. And the purpose here is to encourage richer token representation learning in order to predict the next few tokens. So previously, when we input a token, we predict next token, right? We only predict next token, right?
Yes, right.
Then here, multi-token prediction is trying to input a single token. It tries to predict next token. It also predicts next token. So T1 trying to predict T2, also T3, and also T4. If we set it to a multi-token prediction to next 3, it will predict T2, T3, T4, right? Because it's trying to predict into future token more. So this way we encourage richer token representation, right? If it doesn't contain anything in the future like T3, T4, it won't be able to do that because we are pushing it to do so. So it will try to learn richer token representation.
Right. This is only during training, though.
Yeah, only during training. And then once it's trained, we cut up. We only left the main model as normal.
So basically training the model so it can predict 2 tokens in advance instead of 1. And when you force the model to do that, then it will not just predict next word in the best way like but it will always try to predict the context and train better so that it's got a more advanced, smarter mind to predict so much in advance.
Train the model harder so that like human, we have like future planning more into longer future, right?
Yeah, I see.
So here, there's another thing is this part, this two green part are shared. So the green part in our ordinary transformer, we have embedding layer and the output head. But these two things we put into the multi-token prediction also, so that they are trained more, right? They should be shared because they are doing same thing.
The same thing.
Yeah, doing same thing. We that's the part we trying to make it stronger, right?
Right.
Okay. Okay, so we have main model is the same as transformer. We have embedding layer, then multiple of transformer block, then output head, and we doing the cross entropy loss against the target. So the main model, this hidden state before output will come into this multi-token prediction model, the module, and then combine with the if we say we are at T1, this is T1's hidden state. T1 hidden state coming here, combine with T2 here.
Right.
Then concatenate and project and coming here, which here is similar as here. Then coming out, then involve the next multi-token prediction module, right?
The transformer head diagram on the
Mm-hmm.
second and the third
Yeah.
are just shown as one, but they're actually multiple layers, just like the left one.
You can do multiple, but I think in the diagram, I'm not sure the official how they implement it, but it can be one, can be multiple, I think. Yeah. So let's go through the single token first, simpler version first. So we have token. Go to the embedding. So it embed the token, right, into the DIM, into token DIM.
Right.
Then we go through multiple transformer block, and we have hidden state before we go to the output head. Then this hidden DIM coming out of here, which go through the norm layer. But it also the T2, for example, we are doing this sentence at the moment. This sentence. Let me make it a little bit smaller. Let's say we are doing this sentence at the moment. So token one is cross, right? Cross come in. Then this is the hidden state for cross. Hidden state coming out here into a multi-token prediction module. And this T2 is the entropy, is also into embedding and the embedding of entropy, word entropy, then concatenate with this one, right? We are here. We are trying to help it to learn multi token prediction, but we are not totally depending on it. We just pushing it. I think, in my understanding, it's trying to push. You see here, it's still put into token 2, right? Entropy into embedding, right? To assist the prediction, right? So we are trying to push it, but not totally relying on it, right? Yeah, that's my understanding. Then we concat this one become 2 times of the DIM, right? 2 times of DIM. But we concat the token 1 and the token 2. 2 times of DIM. So we need to project down into 1 DIM. Then we go through the transformer block. Then we go out as normal. And for the for the third token prediction, we also doing similar, right? The same thing. Yeah. So this is a single token version, but in transformer we are doing parallel. So at the same time we put in multiple token, right? In a batch, and in multiple token in a sentence. So this is same meaning, right? Just a multi-token level, multi-token version. Any question?
No, let's go ahead.
Okay. Let's have a look how we implement it in code. This code is also I reference some of notation and also from paper. So I wrote it myself. There could be some misunderstandings here. So okay, let's have a look here, and we have a look in the code here. So this multi-token block, is for the transformer block. Yeah, transformer block. Let's say transformer multi-token transformer block. Okay, so it's a normal thing here. So attention, feed forward, then attention norm and the feed forward norm, right? Then this is the code the same as before. Then we go to the multi-token prediction module. We have shared embedding. We pass in, so it's shared with the main model, right?
Yep.
And the head we also pass in from the main model. Then we add two things. We add some other things, right? The norm and the projection and the transformer block, right?
Yep.
And we according to this diagram, so we do this is current token. So it's this part, the T2 part, and this part is coming from the previous hidden state. So it's coming from here. Previous token, right? So for token 1, when we doing the multi-token prediction, we are here. So this is a T1's previous hidden state coming in, right? And this part is T2. So T2's token, this is T2's token. This is T1's hidden state coming from here, right? So T2, we're doing embedding and embedding norm. So T2, we are doing embedding and embedding norm, right? Here.
Yep.
Then T1, hidden state coming in, we are doing hidden state norm here. Then we concat the two things together. Then we do projection into so that the dimension is the same, right? Then this one going through transformer block, then output head coming out, right? Then we keep the hidden state from the multi-token prediction here out of the next, right? So we hidden state and output, right? Okay, so this is the one-to-one mapping to the diagram. Then we I think we go to the transformer part to understand how we use this multi-token prediction module. Transformer, so we have, except for the normal code, we have multi-token prediction. Here is also configurable. So here, if we say that number of multi-token models, if we say 2 of them, right? We just put it in 2. If we want to predict more, then we put a 3, 4 here, right? Say we only have 2 here. So I omit some of the code, so only left the multi-token prediction. So if a multi-token prediction only used in chaining, right? If we are doing chaining, so this H is the hidden state after going through the encoder decoder. We go through multiple encoding decoding layer. So we have hidden state. Going through the head, we get the node-switch for the north calculation. Then if it's a chaining, we go through multi-token prediction. Multi-token prediction, we need to prepare the input token. Input token, we need to shift the position. You see here, T2, we shift 1 position. If T3, we shift 2 position, right?
Yep.
So let's assume is T2 here is the MTP module 1. So to shift 1, so I is 0, and we shift starting position 1, right? Starting from 1 behind. Then this plus sequence length. This sequence length is already, for the main model, is already considered if we have multi-token prediction. You see here, the main token will not reach the end. It's reaching the end minus the number of the multi-token prediction, right? It's already considered. Yeah, so this one will have T2 token forward for the first multi-token module 1, right? Then this hidden state is coming from the main module. We are doing the first module. If we are doing the first multi-token prediction module, right? Previous state is coming from the main model. Then we going to the multi-token prediction. We going through before. Then for the second, for this module, the hidden state is from this one. Is from this one, right? This is overridden. No longer the main model is coming from this one. And then this token, it will be shifted too, right? Yeah. So we calculated all the node-switch. Then node-switch coming out, then compare with target, right? So it will become node-switch list. Node-switch list consists of the node-switch from main model and the node-switch coming from multi-token prediction model 1 and the model 2, right? It will have a list, right?
Yep.
Okay. Okay, great. Any question?
No, we're good. But how do you reduce the error? Because every time you input a token, you get 3 next tokens from here. and then you just reduce the sum of the total error, or do you
Total of
get,
if during the
if,
training time we have main model nodes and those multi-token prediction nodes, those nodes is similar as the main model nodes. They are all cross entropy nodes, right? It just shift
Right.
by one, position shift by one, right?
That is right, but when you want to look at the total loss from this multi-token prediction, are you going to add the loss for all?
Yeah, add no nodes, then could be you could apply some like factors. For
Waiting.
example,
Yeah,
main model has a higher.
yeah, that's what I was thinking, that you need to apply some weights that you pay
Yeah,
more
wait,
attention to certain, yeah, to
correct.
certain. Okay.
You can. Those are
Do you know what do they apply those weights
uh here
or?
in the paper they don't
Yeah.
mention anything.
Oh, okay.
Yeah, you can have a look if they mention any weight. They may mention weight for the I didn't I didn't notice that part, but you can have a look, see if they mention or not the weight they apply here. Okay, so this is multi-token prediction. Okay, I think that's all for the more all things from the main part here. So the last one left is this one. This one we have some time left, so let's finish this one. So this auxiliary noise. So we said the main measure that is using the bias, right, to adjust the node balance for the experts, right? But in the paper, it mentioned they still using this auxiliary noise, but they give very small weight. Given small weight, because as we previously mentioned, that if we give too large weight, when we add to the main nodes, it may interfere the main nodes, right? So here we only apply a small weight here. Then let's understand the formula. So this one is a little bit complicated. Let's understand the term first. So auxiliary nodes. So there are a couple of perimeter here. NR means number of experts. Those experts refer to the routed expert because in the share part is always going through. So we only consider the routed expert, right? Having the embedded issue. So number of experts, this top K expert, and I here refer to the ith expert, and the T for example here, T refer to token, T's token, and bigger T, capital T here means the sequence length. One is indicator just saying that whether it pick that one or not, indicator function. And SIT is the same as we mentioned before, is the affinity score for token to expert. It's a score. So this one we already understand. This is affinity score for T's token to ith expert, right? We in the source code we calculate this affinity score. We call the score and the plus bias, right? In the source code.
Right.
Yeah, this is exactly that. Then we normalize it. So this term we understand. Okay. Then we try to explain this term first. So this one. Fi. So Fi is the expert relative node. Let's see. If we define an absolute node, so absolute node means number of token expert I received over the total number of token. So out of T tokens, how many tokens that expert I receive? That is the expert absolute node, right?
Yep.
Yeah, the percentage that token processed by expert I. So it's the top K selection indicator divided by T, right? This is total sequence length. So this ratio means absolute node, right? This is the range is 0 to 1. 0 to 1, no problem, right?
Right.
So if expert I is not selected at all, this will become 0. If all tokens go, all tokens for top K is always going through the expert I, then this will become 1, right?
Right.
Then we define a Fi. It means relative node. Those things is my understanding. It could have some errors. So let's follow me first. If you find any error, let me know. So it's I understand it as a relative node. So it's a absolute node divided by ideal absolute node. So absolute node is this one, right? We explained before. So ideal absolute node. Ideally, if ideally, which means is balanced, is uniform. Each expert get equal chance to receive token. So we call it ideal absolute node. So it's equal to K divided by N. So each token, if we pick top K, then an expert will get this chance to receive the token, right? Yeah. Any problem? If for example we reduce K to 1, each time we pick one expert, then it's 1 over N chance for each expert to receive this token, right? Yeah. So if we pick top K, the ideal will be K divided by N, right? So this is ideal. So when we divided this, become relative. This is similar to we are doing like normalization, like standard deviation, standardization, right? Like we did for the for standard normal, right? Yeah, the value minus mean, then we divide it by standard deviation, right?
Right.
Yeah.
Yeah, I see.
Okay. So so its range will be 0 to infinity.
Right.
So this all like a probability. So they are all positive numbers. So it can only go to 0, and it can go to infinity.
Right.
So if Fi greater than 1, if absolute node is equal to ideal node, that's what we expect. It will become yeah, it will become 1. If it's larger than 1, then it's overloaded, right? If it's smaller than 1, it's underloaded, right?
Right.
So why we favor this relative node instead of absolute node? I think we can see now. Absolute node will change if we alter k.
Mm.
But a relative node like the standardized value, it's a relative. It's like you remove the unit, right? It will
Yep.
not change. Yeah, it will not change. Okay.
Mm.
So alternatively, Fi can be redefined as this. A relative node, number of tokens that expert I receives divided by ideal number of tokens expert I receive. So we rearrange this expression. We move T down and we leave only this one up. So you can interpret in this way. Ideally, each expert should receive this much token, right?
Yep. Yep.
Yeah, but actually you receive this much token.
This much.
Yeah. So we can understand as Fi is interpreted scaled absolute load, right?
No.
Also say this. Okay. So this is the term Fi in the paper. Then PI. PI is quite easy to understand. It's the average token to expert I affinity. PI actually is like the continuous version of Fi. Fi is discrete version because we are applying top K, right?
Right.
And PI here is a summation of this score, is this probability, right? Then we average over all the tokens in the sequence, right? So this is a continuous version of this top K, right? This is like probability score, average probability that you token to expert affinity score, average over the whole sequence, right?
Okay.
Then top K, it's picking the top K. So unless your score is reaching the top K part, otherwise you will not be picked. So it's discrete version. Do you guys understand?
Yep, I see.
Okay. So it's a discrete version of this. These two things are tied together. If this part change, this part may change, right? May change. This continuous version of this one. This one, like you try to cut. You try to cut out of here. Okay. So this one is the averaging over the sequence. So it's an average token to expert I affinity score, right?
Right.
Averaging over the sequence. Okay. So we this part is already done. This part already done. This part already done. So we coming to the loss function. Loss function, we can ignore this part. This part is just weight, right? It's a weight.
Right.
The main part is here. So we ignore the scaling factor. We have balance. We have this. So it's dot product between F and P, right? F is a scaled absolute expert node distribution.
Right.
And this is multiple F together, right? And this multiple P together. P is the approximate distribution. No, P is F's approximate distribution. So this one is continuous version This one is grid version, right? But they are somehow connect together underneath, right? So F is tied to P. What we would like is to F to be uniform, right? If F is uniform, then all the routed expert is balanced. So we can design a simple square north like this, right? We normally do. So if F minus uniform, then square north. If we minimize this one, then we want to get this uniform, right? We will push F to be uniform, correct?
Yep.
Yeah. So so we can add P and minus P, right? There's no change, right? Add P minus P. This is like a trick. Then why we add P minus P? Because this one F is not differentiable. Its top K selection is not differentiable. Only P is continuous, so it's differentiable, right? Yeah. Then this derivation is from this link. This link, as I mentioned before, this link is in Chinese, so you can, if you guys want to have look more explanation, you can come here. You can use like Google Translate to get the English version. So this means stop gradient. So we set this part stop gradient so that it doesn't have any gradient. Only this part has gradient. Okay. Yeah, so we have this part minus 1 over n. We want PIs to be 1 over n so that it's uniform, right? Now we want to find its derivative. Okay. Then we do derivative on this. So these two coming down. So this one we keep. Then we do PI to perimeter, right? Derivative with respect to perimeter. Okay. So this part no longer have derivative, so we can this one can minus this one, we can remove it, right? Only this part has derivative. So we remove the bracket and combine these two, cancel out, right? We left with Fi minus 1 over n. Then we do derivative on this part, right?
Yep, right.
Then we can pull the derivative back outside because this part doesn't have perimeter, so it doesn't matter. We can pull it out. Okay. Then we split the two parts. So this times this become this part derivative, and this part, these two parts together we do derivative, right? These two parts.
Right.
Split. And then we can see this part will sum to 1, right? Sum to 1. So derivative 1 is 0, right? So this part becomes 0. So we only left this part. So which means if we do derivative on this loss is equivalent to we do derivative on this. Right? And this is the derivation from here. So it's the official paper doesn't have derivation explanation. They only like 1 or 2 sentence, very simple mention, but there's no detailed derivation. So this is its understanding. So could be wrong, but I think this may make sense to me. Yeah, that's why this formula coming from. Yeah. Any question?
No, we're good.
Good. Okay. 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 Great. I think that I will stop the recording.